morning, everyone. Today, I'll talk about some of the machine learning work that's happening at MSR India, and in particular, some of the things that I've been pursuing in the last few years since the ChatGPT moment that happened. So, before I go into some of the details of the problem and the work that I'm doing, I wanted to give you a sense of AI work at MSR India. And of course, MSR India is a big research lab. It focuses on various things like theory, systems, work at the intersection of AI and society, and so on and so forth. But because my talk is going to be primarily a machine learning talk, I want to sort of showcase the research pillars that is around AI at MSR India. And one of the important research thrusts that we have is frontier retrieval models. So today you hear a lot about reasoning models, right? So you hear a lot about models that are being released by companies as well as in the open source domain. But what people are not focusing on is this problem of retrieval, which is how do you accurately and efficiently retrieve relevant documents from a very large corpus consisting of enterprise data or even the web data for a given query. So here is an example. So Microsoft has copilots like this. If you have Windows operating system, you may have this Copilot app in Microsoft. So typically users, especially enterprise users who are like parts of organizations and institutions and so on, they can ask these kinds of queries. For example, what are the important projects featured in the recent tech summit, right? So maybe I have the context of what the recent tech summit is, and I just want to get a sense of what were the important projects featured, right? And typically these Copilot applications, of course, they use large language models behind to understand this question, to prepare a response for you and so on. But for these responses to make sense, in fact, these large language models don't know the enterprise context. They don't know what tech summit is. They don't know what are the important projects that I have, right? Because these models are trained on the web data. So they don't have a context of what enterprise data is. Which means that the Copilot has to talk to a retrieval engine that interacts with documents like emails, chats, and so on and so forth to be able to ground the responses that this Copilot is going to give. Right? So even though these models are exceedingly good at preparing responses, they know a lot of world knowledge, they still don't have a knowledge about the projects that I work on, right? Which is very personal to me. So which means that retrieval plays a very important role for the success of Copilots. So that's why we are focusing, retrieval is an important focus area at Microsoft Research. And one of the biggest questions that we are going for is, just like how OpenAI and other companies are building these very large models that do reasoning, we ask the very similar questions for retrieval. Can we build a trillion parameter model that is primarily meant for retrieval? That is the goal of the model. It uses all its parameters to be able to successfully and accurately retrieve the documents that the Copilot needs for the LLM to do its job accurately. The second big research area around AI at MSR India is reasoning. The term that's often thrown about these days a lot. Even though we don't fully understand what reasoning is, we only have a sense of what reasoning is. We don't formally define reasoning, but I'm going to stick to the term just because it is familiar and it's in the vernacular today. So the problem is, how do you formalize, how do you evaluate, and how do you improve the ability of language models to reason, plan, and act? And we work at various settings, right? So one setting is interaction with problems. These are problems which are completely closed. Math, logic, and coding, where if the problem is presented to you, just in the context, in the memory of the LLM, you can try to solve the problem entirely without relying on any external knowledge, without relying on any external sources, and so on. So we can completely solve the problem using, let's say, this sort of chain of thought type of reasoning. So that's one setting. The second setting is where you have to go outside of LLM to solve the problem. Imagine settings like software engineering agents, right? So it's not sufficient for the LLM to generate piece of code that you want. You also want to make sure that the code actually runs. It first compiles, right? Which means you have to interact with the compiler to ensure that the code that is output by the LLM is good. And furthermore, not only does it compile, you have to ensure that you can write some test cases and show that the code is actually doing what it's intended to do. So you have to go outside of LLM's boundary to be able to solve the task. So which means that so this falls under this umbrella of interaction with environment. So not only the context of the LLM, but also outside the context of the LLM, you have to interact with tools to be able to solve the problem. And finally, you take the environment all the way to humans, right? So imagine you are using Copilots to solve tasks such as preparing for meetings, right? Or preparing for your exams next week. And then you can say, or writing executive reports for projects. So which means that this has to be sort of a human in the loop kind of a task. The LLM says that, hey, these are the projects I found. Do you think I can write about these things? And the human says, yes, this makes sense. Can you just go ahead and prepare a report for me? And then the LLM goes away for a few minutes or even hours and then comes back with a very detailed report, like how a human would write, right? So we are trying to solve these office tasks that would take humans, experts, assistants, office assistants, hours to do. So can we solve these kinds of tasks with a little bit of nudge and interaction with the humans who are actually wanting to accomplish this task efficiently? So these are the sort of different settings where we are looking at. And in the rest of my talk, I'll focus on these kinds of problems where that involves coding and software engineering. So the next roughly 30 minutes or so, I'll sort of start with the motivation of the LLM landscape and what some of the real world application challenges that are thrown at us constantly, despite the advances of these large language models. And the second part of the talk will focus on the title of the talk, which is robust customization of LLMs. What is the problem we are looking at? Why are we studying this problem? And what are some of the solution approaches that we have developed? And in general, the community has been thinking about. Right? I'll focus on two settings, black box and white box settings. I'll get into the details later on. And finally, I'll end the talk with some open research questions that you can think about as you step into the next phase of your career, and some of the exciting opportunities in MSR India as well as broadly in India. So as you know, LLMs are getting increasingly better at hard benchmarks. You see news articles written every day. When was the last time where you see news articles about machine learning models, right? So we are living through such an era where normal magazines pick up on machine learning models and sort of make news about how good they are, right? So this is one of the. I also want to flash such a slide that says that these models are actually becoming very good. So these are some of the state-of-the-art models: GPT-4o, which is the reasoning model from OpenAI, and the Claude Sonnet, and then Google's Gemini, right? And these are some of the very hard benchmarks. At least these used to be very hard, like MMLU, which is language understanding, and math problems, academic textbook problems. And then GPQA is a recent benchmark. I think it's called Google Proof QA. That is, you cannot Google these questions and get an answer, which means LLMs have to actually work through the problem to solve. And these are grad level science questions, so you can actually read the question. It's pretty challenging, even for an expert in this domain. They will have to use a scratch paper, or they will have to go to textbooks to refer to understand some of these questions before they can. Maybe they also need to do a little bit of math to come up with an answer, right? And of course, they will have an explanation as to why they think the answer is correct. And as you can see, on this GPQA benchmarks and experts, like people who do PhDs in this field, they get about 65% on this data set. And you can see the models are catching up. This dark pink, I think, is GPQA. And you can see the models are already catching up human ability on these benchmarks. And of course, people keep coming up with complex benchmarks. So the most recent complex benchmark is called Humanity's Last Exam. So as you can see, there is a finality to the title of the data set, right? So we want to create the last exam, which is very difficult. And not surprisingly, these models are struggling. Even the latest model is actually less than around only about 10% accuracy. And to give you a sense of how difficult this benchmark is, so this benchmark is classified into different topics like classics, ecology, chemistry, physics, mathematics, computer science, and so on and so forth. And they seek experts from various colleges. These are professors, students, doing PhDs, and they submit questions. And that's how this benchmark was created, about 3,000 problems across domains. And you can see, right, this is a fairly complex question. It is also multimodal, right? There's an image and an inscription, Roman inscription image, and the question says, hey, can you translate it? And it also says, and it wants a translation of this Palmyrene script, and it also asks it also gives a transliteration of the text in case it's not able to read, because I think many of these cases you can evaluate on models that don't understand images as well, which means that this forms as a hint to those models that cannot process the images. And there's another question in ecology. You can read through the question. It's very difficult, even though the final answer is answered with a number. So these benchmarks give a flavor of natural sciences, math, and so on. And even in the coding world, these models are catching up. So one of the most popular benchmarks today in the coding world is what is called SWE Bench, which is software engineering benchmark. This benchmark is roughly about slightly more than a year old. This benchmark started with this question, which is given an issue description. An issue is something like when you go to GitHub, people typically submit issues, right? Like something fails. Hey, I ran this code. something broke, right? Typically you write some description or you say, hey, this is the piece of code I ran and it failed. So it has such an issue description that someone submitted, and then the full code base. It could be as big as a Django code base or a Ruby on Rails code base. So these are hundreds of thousands of lines of code. Right? And then given these two as input, the goal is to produce a patch, which is basically what you will submit to solve an issue that fixes the issue. Right? And usually there are some golden test cases that are hidden to the model that they will run and see if the patch that the model produced solve the issue. Typically the patches apply to some function somewhere, or maybe two functions in two files in the entire code base. So the challenge is to first find which files you have to fix, and then also find the right place where you have to fix, and also try to validate that fix. So it's a very challenging problem. And in fact, when it started on when the dataset was published a year ago, the state-of-the-art model then was GPT-4, and it was even if you told the model that this is the file you have to fix among all these files, the model would only get about 5% accuracy on this benchmark, which means it could not solve 95% of the data set. But look at where the models stand today. In just a year, right? Sonnet is already breaching 60, O3 Mini is breaching 60, and many of these models, and 4.5 is at the latest model from OpenAI is close to 40%, right? This is also a very impressive achievement. So it's all good, right? So these models are actually catching up, and we are also throwing harder and harder benchmarks. So what stops us from using these models day in and day out in all the applications that we are building? The problem is that there are several challenges that arise in the real world applications that in particular these models find challenging in many scenarios, right? So here is one scenario that I'll use throughout the talk, which is a reasoning scenario in Bing search. So the task is to infer if two search queries share identical intent or not. So imagine you're a user typing a query into the Bing search engine, say things like restaurants in NYC. Let's say you're in NYC and you search for restaurants in NYC, and then some other user might be searching for, let's say, restaurants in Manhattan or restaurants in the Big Apple, right? So one of the important problems there is to target ads against these queries, or let's say target even relevant responses to these queries, right? You need to know which queries are identical, which queries are not identical, to be able to give very targeted ads, because they will usually have a training set of some certain number of queries, and the model needs to be able to understand which query is identical to which query, so that it can take the ad for that particular query and show the user. Now this actually turns out to be a very hard problem, because these models have world knowledge. Of course they know NYC is same as New York City. Of course they also know that Manhattan is inside New York City. They may also know that New York is the state of New York City. But in many cases we don't go literally. The world knowledge cannot be applied literally. Sometimes I would say if I search for new restaurants in New York, I would treat that query to be same as restaurants in NYC, because oftentimes I don't spell out city. Even though city is in my mind, I'll always say restaurants in New York, just because I know that the model will assume that NY means NYC. So there are lots of connotations in the way we interpret the system, we query the system, which means that the world knowledge of these models are not going to help at these are kinds of precision tasks. These are surgical precision tasks, right? I need to know which queries are identical. So the world knowledge is not going to help. What is going to help? Experts are going to help. Experts can create labels. Experts know that, hey, this query and this query are identical because I've been in this field for several years. I know that this is how these queries, I have domain knowledge to say that these queries are identical, right? But scaling these, ideally what I should do is that I should get these experts to create these labels for many queries and then be able to improve these models. But it's a challenging problem, because how many labels can you get, right? Even if you crowdsource, right? I really cannot crowdsource, because I really need experts in this particular domain who has been in this ads field for a long time to be able to generate these labels, which means that it is a challenge to create quality labels to be able to improve the performance of models like GPT-4. And secondly, GPT-4 is also by itself cannot solve the problem, because it depends on cultural and geographical biases, right? The same question the same two queries can have identical connotation in the US, but not in UK. For example, cricket, right? It could mean something in UK, which is very likely the game of cricket, whereas in USA it may not mean the game of cricket. It's very likely to mean the insect. So these biases creep in, so that you cannot just label two pairs as yes or no. It also depends on what geography these questions are asked, who is asking these questions. So there's a lot of things that go behind these scenes that it's very difficult for models like GPT-4 to just blindly apply the world knowledge it has to be able to infer the answers. So if you do simple few shot, like if you extract some labels, like if you extract some labels from humans and then put those labels in what is called the few shot prompting. If you attended Sunita's talk yesterday, she talked about this in context learning, right? So you can put those examples in the prompt of GPT-4 as saying that, hey, these two pairs, they're identical. These two pairs, they're not identical. These two pairs. So you can just create these list of examples and then ask the GPT-4, hey, now for this new two pairs of questions, the new pair of questions, can you tell me if they're identical or not? So you can write this prompt, but this prompt is not accurate. This strategy is not accurate simply because it's very difficult for the model to generalize, because the questions that you have picked to put in the prompt, the examples you have picked to put in the prompt often will have some bias. They'll be from some market, some geography, some type of questions and so on, and GPT-4 can easily latch on to those biases, and by latching on to those biases, it's not going to generalize. So that's why this problem is very challenging. So despite these models getting better, there are these tasks that keep coming on everyday life that somehow surprise these models, right? Another task that I'll talk about is what is called software engineering in copilots, in code copilots. If you use VS Code and GitHub and so on, today they have copilots everywhere. And so code editing, editing code to satisfy what is called non-functional requirements. Typically, if you look at the benchmarks, what do they ask, right? Hey, produce a code. Here is a test data. If the code runs on the test data, you're good. If the code fails on the test data, you're bad, right? So this is what is called a functional requirement. You just test for functional. Does this code sort the array? You can check if the code sorted the array, you're done, right? But in real world, when I deploy these models in the copilots, the developers look for various other kinds of requirements, not just functional requirements. Okay? They look for what is called non-functional requirements. Things like, hey, this is a code that sorts the array. Can you make this in place? Can you improve the complexity of the algorithm? Can you make this more memory efficient? Can you make this streaming instead of batching? So these are the kinds of questions that people ask, and these are refactoring kind of questions, right? They're not functional. They're beyond functional. You look for a certain non-functional aspect of the code, and how do you even test that non-functional aspect of the code? Right? First, you have to show the equivalence of the code. The code that you generated also sorts the array, but it sorts it more efficiently, right? So it's a very complex problem to even specify. So therefore, the models also struggle. And in fact, we put together a benchmark that consists of these kinds of examples. Like, so here is this is a real code from an Android repository that the developer is trying to do is trying to optimize bandwidth usage, because this piece of code is going to run on your app. So it helps to optimize bandwidth by, let's say, not downloading a file if it already exists, right? So these kinds of optimizations people do all the time, and this and the kind of benchmarks that people evaluate, they don't capture these kinds of scenarios. So we went ahead and created such a benchmark. This is another example where
I'm just curious, why are you calling this as a deployment challenge?
This is a deployment challenge because one of the places where we want to deploy LLMs in Microsoft and in general is places like GitHub, where people create these kinds of issues. And a lot of issues that people create are failures, not just because, let's say, a feature. Very few of the things are things like, hey, add a feature. But many of these cases are refactoring type of things. Hey, I want to rewrite this code.
So you just mean the benchmarks are missing some real life scenarios.
The benchmarks are missing some real life scenarios. And the benchmarks, even if the models do very well on those benchmarks, it doesn't mean that when you apply them on real world scenarios where you face problems like refactoring and security. This is another example, security. You want to do this try catch, you have to raise the right exception and so on. So these are important things that people care about in deployments. And these are not functional in the sense that I cannot write a test case to show that, hey, you've done it correctly. I mean, of course you have to pass whatever test cases this passes, but you have to do something more than that, right? So that more than that is what real world deployments require, and these benchmarks don't capture that. And we did go ahead and create such a benchmark called No Fun Eval, which is a pun on non-functional evaluation. And we showed that leading models, in fact, struggle to do well on these kinds of benchmarks. And there are several blind spots of these large language models. In fact, we could very clearly see that accuracy is significantly worse on these kinds of tasks than on functional tasks. Like all the bar charts that I showed you where the accuracies are breaching the human level accuracies, they are true for certain type of tasks, but for these kinds of tasks that we are interested in, and in fact we should, as a community, should be interested in, their accuracy is significantly worse. And even O1 is actually not much better than GPT-4, but in general you see that O1 is almost always better than GPT-4 in all the values. So I'm moving on to, so now that we sort of understand some of the challenges and some of the deployments, issues and things like that, I'll talk about some of the work we have done in sort of making correctional sort of actions towards these, right? So what do I mean by customizing LLMs, right? So typically, what do you do, right? So you have an LLM checkpoint either via OpenAI. OpenAI gives you an API, or Anthropic gives you an API. So that's one way of accessing the models. In some cases, you might have the model itself if you're using a Llama model, which means you can just download the model and start using it. So, but however you typically start with some checkpoint of the model, and then you have to take this. You have to go from here to some deployment, right? The model is actually sitting inside an application like Copilot, right? So in the black box setting, which is probably the most common setting because we are often behind an API like OpenAI, the best thing you can do to customize these LLMs is prompt tuning, right? So which is, I don't have access to the model weights, so but I can at least try to improve the prompt so that it does better on the task that I care about, right? So if you recall the first scenario I talked about, which is the Bing search scenario, where the goal is to identify if two search queries are identical of intent or not. This is a very good example of this setting where OpenAI's models are sitting behind some wall, and the only thing I can do is to improve the prompt that I can write, right? And I also told you that the in-context learning, standard in-context learning does not work. So the question we want to ask is, can we go from a simple one-line task description, which is, hey, identify if the two queries are identical or not, just that one-line English description of the task, to a detailed human-like prompt, how a human would write. In fact, I'll show you how a human writes this prompt. So in fact, there are engineers in the company, not just in our company, every company, who write these kinds of prompts, which are very elaborate. These are like pages and pages of prompts. They write detailed things, and it helps to write this level of detail, right? So things like, hey, you're an expert in Bing search domain. Your task is to convey if the two given search queries asked by real users in the Bing search share identical or not, and blah, blah, blah. And then you will have paragraphs talking about corner cases, what gotchas, what is important, what is not important, right? Things like, hey, you have to focus on brand specificity. You should identify two queries as identical only if they talk about the same brands, even if they slightly differ in the brands. One is talking about iPhone 15, one is talking about iPhone 16, then I should not consider them as the same query. So you have to impart all these things where prompt, and humans actually they spend weeks writing these kinds of prompts and testing it against data to see if it gives them slightly better accuracies and so on and so forth, right? It's a very laborious process. So one of the things that we did recently is sort of mimic what humans do using LLMs. So we tried to answer this question, you just using LLMs and using these kind of gradient descent kind of algorithms, but on text data, can we go from one line task description to a nice elaborate essay like prompt, which with detailed sections and examples and things like that, right? I don't know if you can read this, but typically these prompt optimization methods work very much like SGD, right? How do you do SGD typically? You have a training data, you have a model, you first apply the model on the training data, compute the loss, and then wherever so you basically try to go in the direction that minimizes the loss, which means that you typically form a batch of examples, compute the gradient, and then take a step in the negative step, and then you iterate. So this is how you do it. You can surprisingly do a very similar thing on text, right? So that is what you can do is that you take an example, let's say the question, this is a different data set, it says, tell if the following is a hate speech or not. This is a hate speech classification data set. And then you give those examples to an LLM, and the LLM says, hey, LLM will make some correct predictions, some wrong predictions. And then you take the wrong predictions and then you give it to an quote unquote expert LLM, which could be another instance of LLM like GPT-4. And you can ask, hey, these are the examples that it made a mistake on this batch. Can you give me a corrective edit to the prompt so that these mistakes go away? So the LLM says, hey, you know what? You did this. Maybe you should try to add this. So LLM gives for each example, it gives you suggestions. And then you ask this LLM to take the initial prompt and the suggestions and apply it. This is like the actual parameter update kind of step, right? So this is the gradient step. This is the update step. It's very mimicking the real continuous world things, but on the discrete world. And surprising that these kinds of algorithms actually work, and people are actually trying to build theory. In fact, I saw a paper called TextGrad from Stanford that does exactly this, but it builds a whole theory, just like how in TensorFlow and PyTorch you have this backpropagation for neural networks. Now Stanford had built a very similar pipeline for text, just dealing with text, and guess where it appeared? This paper. It appeared in Nature. So these things are being considered as fundamental science. These kinds of machine learning algorithms today are being considered fundamental science. So we do a very similar thing, but we make this one observation that maybe it helps to batch these wrong examples to identify why they are going wrong. That is, we try to cluster them. We cluster like failures. If certain examples failed in the same mode, if they failed for the same reason, we try to cluster them. And we ask the model, this is like something like mini batching. Right? If you're in SGD, you do this mini batching. And then we try to get feedback for each of the mini batches, hoping that for the examples that are similar within the batch, the feedback is also likely to be similar. So you get similar feedback. Hey, for example, this one you could say that, hey, you should add a section on racial discrimination, right? Because that's an important part of hate speech. And then maybe these examples will say, hey, you should add a section on general articles on violence, right? So it can come up with very precise feedback for each of these like examples, and then the expert LLM can then give very precise edits to your prompt, and then you can finally aggregate them and apply the edits. And again, going further ahead to SGD and applying these sort of mini batching and so on further improves the accuracy of these prompts, and we're able to actually get prompts that are very human-like. I'll also talk about the white box setting where you have access to the full LLM. Right? So far, we were in the setting where you only have AP access to the model. But now, let's say we are in the setting where you have full access to the LLM because these are, let's say, open source LLMs, which means you can change the weights of the model, and let's say also have the compute to do this fine tuning. And if you look at the white box steps, right? So I also wanted to just sort of have an instructive slide that tells you about how typically people go about tuning these models, right? So, for example, if you're in OpenAI, this is what you would do. So this is how they, for example, created GPT-4. So they start with some web data, and then they pre-train the LLM. By pre-training, this again sentence completion loss, next token prediction, right? In almost in all the cases, the loss is almost always the same, which is next token prediction. And then once you have some base model, then for the application or for other reasons, you may want to fine tune the model. That is, which means you will collect more data, more sort of supervised data, more principled demonstrations, that the kind of data that users will want to use the system. They'll create such data and then further fine tune these weights, arrive at a different checkpoint, and then in 2022 this thing happened. What I call the ChatGPT moment happened, right? They realized that you can not stop here, but you can go further and generate responses from the model, because I'm going to deploy this model, which means that I want to understand what kind of responses come out of this model. And then you can generate sample multiple responses from the model and give it to an expert, a human expert. Hey, which of these responses do you think are the better ones? Give me a ranking of these responses. They take this feedback and try to further improve this model in a contrastive way. Hey, this response is better than this response for this question. This response is better than this response for this question. They realize that by doing so, they can actually deploy these models to the end users. Things like in ChatGPT, where users ask questions and the model can in turn try to be accurate, try to be polite, try to be helpful. So so this training made ChatGPT possible, and this pipeline, the first ChatGPT that came out in maybe end of 2022 was by such a pipeline. And of course, sitting in Microsoft, if I want to build applications, I have to take this checkpoint and see if it's good for my application, or should I do something more so that I can make this even better for my application. So in this talk, I'll talk about this part, some of the efforts that we are doing in this part of the pipeline, which is the fine-tuning part of the pipeline. And I'll focus on that scenario, the second scenario, which is software engineering copilots. So the problem is this: I want to customize code LLMs for code editing. So code editing is a very particular scenario among all the things that you can do with code generation, code summarization, code understanding, and so on and so forth, which these models are pretty good at. But code editing is a very specific scenario where the full code is given to me and some instruction is given to me saying that, hey, can you make these changes, right? Or can you make this better? Or can you make sure that this error goes away, right? So you have some expression of intent and the code is given to you, and the goal of the model is to output pretty much the same code, but with the edits that you want, right? Which means that there has to be preservation of functional correctness. functional equivalence. At the same time, the model also has to achieve the task that you want to do. That's why it's a slightly different downstream scenario than what these models are actually built for. And of course, you can imagine applications in VS Code, Visual Studio, and other places. And this is a one-slide summary of what we have done in the fine-tuning stage that I showed you. So we are able to take many of these open source models that are out there, which is state-of-the-art, like Quen Coder 2.5, which is one of the state-of-the-art models for coding. Models like DeepSeek and so on, and we are able to improve them. We know that these models struggle in the benchmark that I initially briefly talked about. Right, there's no fun eval, which is evaluating on the non-functional aspects of code. These models do struggle, continue to struggle on those benchmarks, and but we are able to consistently improve every model in the family by fine-tuning using our algorithm and our data, and able to produce better models that are better in very precise sense. They are better in the code editing tasks that we want the model to do, and they're also better in the original sense. That is, they also do the tasks that they originally did well, they continue to do them well. So if you attended Sunita's talk yesterday, she mentioned two kinds of things when you talk about robust adaptation. One is you want the model to do well on the task that you're helping the model to do better, and by doing so, you don't want to overfit. Right? You also want to make sure that the model originally, if it was doing better on 10 other tasks well, you want the model to continue to do better on 10 other tasks, only that you also want it to improve on the 11th task. Right? So you can think of code editing as the 11th task. So we show that not only is it doing very well on the 11th task, but it is also doing as good or sometimes even better on the original 10 tasks, which I think is the success of this work. I have the details of how we got to this results in the slides. Maybe you can go through this. I'll spend some time talking about, or if during the questions we can come back. I'll spend some time talking about some of the open questions that are in this space, right? And then maybe, if time permits, I'll give you some sense of the method itself. So many open questions are there. So one is, can we improve the quality of edits with test time compute? Because you're saying these models like over and R1 style, if we allow more time for these models at test time, like you say that, hey, this is the piece of code I want to edit. This is how I want edit to be run, but take 5 minutes if you want. Take 10 minutes if you want. Come back with a very good edit for me, right? So how do you train these models to capitalize on the test time? The fact that you have more compute available at test time, can the models capitalize on it to come up with better and better quality edits? This is a very important question. So this question is not just with respect to edits, but also you can ask this question with respect to any reasoning task that you want to do. This is one of the sort of hot areas in research today, which is this test time compute. And the second one is, can we do similar robust adaptation for general models beyond code? You take any reasoning model out there and you have some scenario in mind. Let's say you want to solve some problems with respect to, let's say you have some domain in math or some domain in chemistry that you find that the model is struggling. You want the model to improve. But can I do a similar adaptation such that it improves on the domain that you are improving? At the same time, it preserves all other goodness, which in general it has. So how do you? And the algorithm that we have is general. So I didn't have the time to talk about the algorithm, but maybe I can. You can look at it. I have given references as well. And finally, an important question from a verification point of view is that how do I know that the edits that the model is generating are good, right? Can I verify the edits? I use the word verify in a very formal sense, right? If you attended the keynote talk yesterday. So can I leverage formal methods to make these edits, and can the models ascertain some guarantees about the edits they are making? So that's a very important research direction from an intellectual curiosity point of view, but also from a very impact point of view, because users will always be happy if you just don't show the code, but you also give a certificate that, hey, this code is actually correct. And of course, you can, if you want to work on these problems, there are many ways you can work. Like Professor Varsha said, like you can, now you're at a point where you want to think about the next phase, and you can work on these kinds of problems, whether you do masters or PhD, or we also have a program called Research Fellows where we take fresh undergrads and prepare them for a career in research. And you can think of this program as roughly the first 2 years of a good PhD program. And in fact, a lot of the results that I showed is working with people like you who have come from IIT Bombay and worked with us. And we have some great students who've worked on several of these problems, and they're all the lead authors on all the papers that I write. So I'm very happy in working with these people. And so I'm hoping that these kinds of seminars and conferences encourage you also to take these paths. And RF is research fellowship at MSR India is just one way to achieve to your destination, but there are many other programs in the country. You should apply to all those programs. And if PhD is what you want to do, then you make sure that your resume is strong enough so that you land in the program that you want. To summarize, so the real-world LLM deployments throw new and hard challenges, and benchmarking and the leaderboard numbers that we often see can only help to some extent. They're not fully reflective of the ability of these LLMs or the inability of these LLMs. And robust adaptation of language models is an exciting research area, and it's critical to the success of these deployments in real-world applications like copilots. And finally, it's a very exciting time to be doing AI research. Of course, it's also a scary time because you see lots of uncertainties, new breakthroughs every so often, but so be it. Thank you.
So I'm Imanshu. So in the first slide, we have mentioned about frontier retrieval models, right? So on 18 March, Microsoft released a fantastic research on something called KBLAM, knowledge-based augmented language models, that particularly claims that there's an end of RAG and in-context learning. And there's a fantastic approach where they are integrating the knowledge sources directly into the attention layer, which they call rectangular attention mechanism. Yeah. So like, what's your view on that? Like, is this the end of retrieval or RAG, and how it's going to be looking like in the next couple of years?
So RAG, right now RAG seems indispensable because a lot of this data is sitting in some private repositories, private code bases, emails, and so on and so forth. So it's unclear how much you can improve the models by integrating this data at the heart of the models, like while training and so on, because there are a lot of concerns like privacy and so on and so forth, which interferes with some of the things that you really want to do. So today RAG seems to be the sort of cleanest and safest way to do these things. But of course, I mean, as researchers, we want to try new architectures that support these kinds of ideas. But right now, it feels more like a research idea. But I don't know if it actually pans out.
Hello, sir. Small thing. Usually, an anatomy of a prompt usually consists of goal, return format, warnings, and content dump. Now, even like take a model like Copilot or Gemini. Usually, these models tend to hallucinate. Even writing it in this format, you said people write prompts for weeks, right? So, how do you prevent that hallucination actually?
The reason people spend weeks to do this is to exactly avoid hallucinations, right? They elicit certain rationales, certain reasoning. So they put all these things in the prompt so that they nudge the model to do what it wants to do as best as it can, right? And of course, it is a model; it is subject to failures. So the only thing we can do is try to improve these models and catch as many mistakes as we can in the prompting stage. And if you want to further improve it, then you really need access to the model itself, right? Mm-hmm. So you need guardrails in the model. You need to be able to change the weights of the model. So in the black box setting, you can only do so much. By prompt tuning, you can only do so much.
Yeah. Thank you.
In the improvement that happened from 5% to 60%, what really changed in that 1 year span? Is it like the model was exposed to more code data, or some architectures changed?
This is I did not talk about it. So we have two ingredients that we attribute to the success. One is we create synthetic data. We have a very sort of rigorous pipeline that generates data that from the get-go has these properties, has these refactoring properties, and so on and so forth. That's one part of the story. The second part of the story is that we have a new algorithm that improves on algorithms like SFT, LoRa, standard algorithms that invariably end up overfitting because there is a lot of discrepancy. If you look at models like Qwen and DeepSeek, they're trained on, let's say, 20 trillion tokens. Mm-hmm. And the synthetic data that we are able to generate for code editing tasks is in the order of billions. Even if we scale, we cannot scale more than, let's say, a few billions, right? So this is several orders of magnitude different, right? So this is where all the machine learning, bias variance, overfitting, all these kick in. So we have an algorithm that tries to alleviate this to some extent, so what our algorithm is a variant of SFT, but it has some nice properties. And so the synthetic data as well as this algorithm together is able to do this.
Also in non-functional tasks, what is the evaluation metric? Is it like conventional text metrics like Blue, or?
So we have an upgraded version of Blue for code diffs on code diffs. And second, in some of the tasks, we actually invoke static analysis tools. So we run a CodeQL and ask if the fix does not have the issue. So we have various metrics.
One thing is from yesterday, I have been waiting to ask, when you all mean robustness, what's the metric?
So robustness, in most of these, at least in ML setting, robustness is usually, it can mean multiple things, but most of the robustness that you heard today and yesterday's Sunita's talk is what is called out of distribution robustness. That is, you're training these models using some samples from some setting that I want. In this case, let's say code editing. I create some synthetic data, which I think is representative of what my eventual goal is. But my benchmarks can look very different than the data that I'm mimicking, right?
So when you do say accuracy, you know that the benchmark is in your distribution. And when you say robustness, you are throwing some like
it means that you're training on either a very small subset of data, which means you will incur the sampling bias and so on.
Okay.
Or your data, I have no idea what these test benchmarks are, but I know that because it's focusing on certain type of tasks, let me mimic those benchmarks and hope that if I train the model on this, I will be able to do better on that. That is the kind of robustness with that.
So one thing, overall, again, very basic question about all of the accuracy and SOTA things that you were showing. This 70-80% and all of that, sometimes it doesn't, the benchmarks and the ways to rate LLMs don't captures the ridiculous things they fail on. Yeah. Okay. So is there a way to quantify that? And because humans, that's such a big divergence from humans that when a human is trained and skilled to do something, they are simply never going to fail on some really silly, we see this in code a lot. Yeah. We have many examples where we are just stunned at the output of the LLM that how could it fail on this? So, has there been any way to quantify that?
Yeah. So so I did not go into these details. In many of these cases, we dissect these numbers. So for example, one of the ways we could dissect these numbers is, if I take the test data and split it into, let's say, very small files and very large files, right? So how is the accuracy similar? Ideally, I would expect the model to succeed on easy tasks and fail more on hard tasks. And if your performance matches this thing, then you're actually moving in the right direction. In many cases, what you find is that your accuracy is, let's say your accuracy is 50%, you are 50% accurate on easy tasks, you are 50% accurate on hard tasks. That's actually not a good setting, right? What we find is that you are, let's say, 60% accurate on easy tasks and let's say 40% accurate on.
Thank you, sir, for this interesting talk.